we will be able to estimate this point or this parameter theta. And once this theta is known to you, so it is like y is equal to a0 plus a1t plus a2t square, and a0, a1, and a2 is known to you. So if a0, a1, and a2 is known to you, you give me any time t, I will plug that value of t into my equation, and I will tell you this was the force. So basically, once theta is known, I can use this expression to find out f, the forcing vector, at any time t. I can use this expression to find out x at any time t. So with this exercise, like 3-4 equations, what I have done here is I have developed a framework that can be used given certain sensor measurements. So this framework can be used to estimate the forcing vector and the state vector jointly. And this is based on the physics of the problem, because this from f to x, this transition was based on the physics. So that is why we call it the physics informed Gaussian process. So the physics is being satisfied. Now, if by chance any of you are interested in knowing the maths behind it, there are like 50 equations using which these things can be derived. So if you are interested, you can have a look into the paper. This paper I have given it here to know more details. And this physics informed GP is also known as Gaussian process latent force model. So the idea is to identify the latent or hidden force on an unobserved force. So you can have a look if you want to know more about this, how we arrive at this point. Okay, so now let us try to solve some problems. So suppose we have a 10-story building. Each floor of the building is represented by a degree of freedom. So this is like a shear building. We only have acceleration measurements. So we don't measure the velocity and the displacements. And then whatever we measure, we contaminate with certain noise, 10% white noise. And the data is sampled at 100 Hertz. And then, so what we propose is a physics-informed GP for force identification, but there are other methods in literature for force identification as well. So these are the 3 methods for force identification that are there in literature. Now the force that is being acting, that the system is experiencing can be of different form. It can be an impact load, it can be a harmonic load, it can be a seismic load, or even it can be some random vibration. And measurement can be complete, like you have measurements at all the degrees of freedom, or you may have measurement at only certain degrees of freedom. So these are the 3 cases that are possible. Now, all the results are there in the paper. I'm only going to show you certain results. Basically, I will show you the harmonic one and the random one with partial measurement. So, okay, so here are the results. The first row shows the result corresponding to harmonic load. The second row shows the result corresponding to random excitation. The left column is the force estimation. The right column is the state estimation. And then there are different colors you can see. So the red color is what we have proposed, the physics informed GP. The black one is the ground truth. So that is the true value that was happening there. And then there are other methods such as DKF, AKF, and AKF-DM. Those are shown by magenta, green, and blue, respectively. So let us come to the force estimation for harmonic load. You can see that the black and the red one have superimposed, while the others are giving erroneous results. So you can clearly see what we have proposed or what we developed was superior. So you can use this method for an actual system and go and estimate what force it was experiencing. For random excitation, and this is a very difficult problem. You think of it, look at this time series of force. It is like some white noise. This is a white noise actually. So it's like seismic also, you can think of it like that. And again, you see the black and the red one has almost superimposed. Blue is also giving somewhat reasonable result, but it is still off by a while. And then DKF and AKF are completely off. So they completely fail. So the take home message from this, whatever I have discussed until now, is that machine learning or in this case Gaussian process, can help us in identifying force of a system just by measuring displacement or acceleration or velocity at certain degrees of freedom. So this can help, and this can actually outperform the usual methods. That is the take-home message. Now, I have not given the time here. You will see that even with computational time, this is quite fast. This force estimation takes for this system took what? If I'm not wrong, a few minutes, like 1 or 2 minutes, and that is it. So you can do it accurately and very efficiently. So that is it for the first part of the talk. Like 1/3 of the talk is over, kind of. You can think of it like that. And that was on Gaussian process. Now let's forget about Gaussian process, and now let's go to neural network. Or to be more specific, deep neural network or deep learning. So what we are trying to do now is, you see, essentially whatever problem you are solving as a structural engineer is essentially a differential equation. So you already know the equilibrium equation, del sigma xx del x plus del sigma xy del y plus del sigma xz del z is equal to, plus body force bx is equal to 0. So, and then you write it for y and z, and that is your governing equation. So when you're using finite element method in abacus or ANSYS, that is the equation that you are solving, knowingly or unknowingly. So that equation is discretized, and you get Ku equal to F. And from there, that linear equation, you basically find out U by K inverse F. But if I go into the basic, you are actually solving a differential equation. Think of a plate. You are solving a plate in abacus or ANSYS just by discretizing it. But there is a theory behind that plate. There is a fourth other differential equation that you are solving. Think about even a beam. So you know about Timoshenko beam theory, Rayleigh beam theory. So even for a Mendelian beam theory and all the Mendelian plate theory, obviously. So like that, there are like differential equations associated with all the problems that we solve. The only thing is, because you have a software or something like this, you don't bother about those equations. Finite element equation or finite element method actually solves partial differential equation. Finite element method was developed for solving partial differential equation. So the point here is, whatever system we are solving, either using finite element method or using some software, we are in essence solving a differential equation. Now, what we are going to look into now is how neural network can be used for solving differential equation. And that is what physics-informed neural network is. But that is not the motivation. The motivation was that when you train a neural network from data, it performs very well. But the point is, when it does not satisfy the physics of the problem. When you are taking this partial differential equation and solving it using neural network, the physics of the problem is satisfied. So basically, you can look into this thing in two ways. How can we ensure that neural network satisfies the physics of the problem? That is one way of looking into it. The other way of looking into it is, can we solve differential equation by using neural network without generating data? And that is another way of looking into it. Anyways, whatever way you look into, that will bring us to the concept of what is known as physics-informed neural network. Now, let me tell you upfront that this is not a method that we developed. The concept was already there, and if I am not wrong, or if my knowledge is complete, this thing was actually proposed in 1992. So not today, not 5 years before, not 10 years before, 1992. That is when this method was proposed, like 27, 28 years ago. But no one paid attention to this method at that point of time, and rightly so. It was not possible to use this neural network with first principle at that point of time. Now times has changed. Now you can use this. At that point, this was irrelevant. So from a research point of view, this also has something important message for us, that what you are developing now may not be useful today. It may be useful 20 years from now. But in any case, what is this physics-informed neural network? This is a very catchy term nowadays, but the idea is not new. This is the same old idea that we are revisiting with modern computational tools. So anyways, let me define the problem. So you see here, del t of u plus some nonlinear function of u. Let us say this is my differential equation, that del t of u plus some nonlinear function of u is equal to 0. This is my differential equation. And the question I'm asking here is, how can I use neural network to solve this differential equation? And that is the plain and simple question. Now, for a moment, let us forget about neural network. If I give you this equation and ask you to solve it, what will you do? Simple. You will assume u to be some polynomial function. Again, a0 plus a1x plus a2x plus b1t plus b2t square, something like that. And then you will plug those whatever assumption you have made into this equation and try to minimize the residual. And by that, you will try to find out the unknown coefficients. In some sense, that is what old tools for solving neural network and for solving differential equations used to do. And in some sense, even finite element minimize the residual in a different sense, but it is still minimizing the residual, which is basically it is trying to, if the residual is 0, you have the exact solution. If it is not 0 but very small, you have the approximate solution. Now that is what we do using basis function. How can we solve this equation? By using neural network. Simple. Just pay attention to this expression. U is a function of time t and x, which is a spatial variable. So what I'm going to do is, I'm going to assume a neural network, a feed-forward neural network, where the input is x and t, because u is dependent on x and t, and the output is u. And then this is the neural network architecture. So these are like nonlinear function which maps t and x to h. So there is some nonlinear function here. Again, there is some nonlinear function here and nonlinear function here. So like you can think of it like collection of nonlinear functions together. And that is how you go from t to x. So u is a function of t and x, and we are assuming it to be a neural network, which is basically a highly nonlinear function. But the important thing here is that u is a function of x and t. And if u is a function of x and t in this architecture, what we can do here is we can take derivative of u with respect to t, and we can take derivative of u with respect to x. So from this diagram, neural network diagram, you can think that we can use chain rule. Del u by del h1, del h1 by del h12 by del h11, del h11 by del t. So that is basically nothing but del u del t. I mean, I just took the one path, you have to take the other paths as well. But that's essentially what it is. You can find out the derivative of u with respect to t. And if you do that, you will realize that the network architecture will still be the same. So for example, if you calculate del u by del t from here, del u by del t will have the same architecture. What will change is these functions, the nonlinear functions will change. So if it was exponential of ax, you are taking a derivative, it will become a exponential of ax. So that is what will happen. So the take-home message is you can take derivative of u with respect to t and derivative of u with respect to x. So you do that. And then all those neural networks like u dot, u double dot, ux, uxx, like derivative of u with respect to x, double derivative of u with respect to xx, all those things you can take and plug into this equation. And what you will get is a neural network such as this, which is shown on the right-hand side. And since this is a neural network representing the differential equation itself, we call this neural network as the physics-informed neural network. So mathematically, what we are doing, this is a nonlinear function. So that is f theta of xt. So this is a nonlinear function. We are taking derivatives and all those things. And then those derivatives, what we are doing is we are substituting into this one, the residual. And if you substitute, so you see here, the derivatives have been substituted, like f theta and derivative of f theta with respect to t. Substitute it here, and what you get is r theta. And that is your physics informed neural network. Again, the important point here is that theta is shared. Like in Gaussian process, the theta is not a function of time. Theta is not a function of x. So if you take derivative, that will come outside the derivative. So theta is not going to change. So this is your neural network that you have assumed. This is the physics informed neural network. And now all that is left is to minimize this residual to find out what is theta. If you are able to minimize or take this residual to 0, you have the exact solution. And if you cannot do that, you have the approximate solution. And this is what we do with the basis function as well. Now, if we are doing that, and if this idea was proposed in 1992, what was the challenge? What has changed from 1992 to 2020? What changes have taken place? Well, what has changed is people in 1992 were very hardworking in nature. We have become lazy. We are lazy people and we don't want to do these calculations. So, for example, if I ask you to do this or ask one of my students to compute del U by del T with hand, he will probably leave the PhD program and say goodbye to the PhD program. So we have become lazy. And rightly so, because we don't need to do these things by hand. We have modern softwares which will do it for us. So we have methods known as automatic differentiation, which can give you this derivative of u with respect to t and x. So we will use those automatic differentiation scheme. And then for solving this neural network, we have TensorFlow and PyTorch, and we can do those things. And I will show you in a slide or two that this is not a problem which needs heavy programming from your end. Solving this problem is actually trivial, and it can be done with 10 lines of code, 10 lines. Yeah, if the problem is difficult, maybe 30 lines, but that's it. And I will show you. So anyway, so here is the summary. So what we do is we assume the solution of the differential equation to be a neural network. And then we represent the residual by using another neural network, and that is the physics informed neural network. And all the derivatives that are needed, we do it using automatic differentiation. And then we formulate a loss function. So this is what we want to minimize. And we minimize it to compute the weights and biases, that is the parameters of the neural network. So there is LP. LP is basically here representing the residual. So that is basically the physics informed loss function, you can say it. And you see there is a summation over 1 to n. So that means I have generated random points of x and t. N random points of x and t in the domain. And then there is this LD, which is data driven loss function. Now, what is the data in this case for a differential equation? What is the data that is available to us? Is there any data available to us? Yes, we have data. The boundary condition and the initial condition. So those boundary condition and initial condition, whatever data you have there, that will go here. So this term will ensure that your boundary condition and initial conditions are satisfied. So basically, whatever output the neural network is giving you should match your boundary and initial condition. And this part ensures that your physics, the governing differential equation, is satisfied. So that's why there are two parts. One part ensuring that the governing differential equation is satisfied. The other part ensuring that the physics of the problem is satisfied, so that the boundary condition and the initial condition is satisfied. So LD is data, LP is physics. Let us see one small problem. So this equation you see here is the Burger's equation. So this is a highly nonlinear equation. So U, this is the nonlinear term here, U times UX. So UX is derivative of U with respect to X. UT is U dot, that is derivative of U with respect to T. And U double X is del 2U by del X2. And then this is your initial condition, this is your boundary condition, and this is your problem domain. Now for this, what is my residual? This is my residual. You follow the cursor, this is the residual. So if this is your residual, and this is what we want to minimize. And then I showed that this is a 10-line code. This is the code written for this solving this problem. This problem, if you want to solve it, this is the code. Directly a screenshot of the code that was run in Python. So it's not difficult at all. These terms are classy or may sound fancy, but if you are working on it, it's not difficult at all. Yes, knowledge of vector algebra, knowledge of probability statistics is needed, but the coding part is at least not difficult at all. Anyways, so this was the problem. Let us see the results. So this is the result. What I've done here is along the horizontal axis, we have time t, so 0, 0 0.2, 0 0.4, and so on. Along the vertical axis, we have x, which goes from -1 to +1. And this is, and we have plotted the contour of the solution. One thing. Second, you see the crosses here, the crosses on the boundaries. So these are your initial conditions. And these are your boundary conditions. The crosses that you see at the top and the bottom are the boundary condition. And those you see on the left-hand side are your initial conditions. And then if you think about training a neural network directly from this initial and boundary condition, you have no hope that you will be able to track this sharp change in the gradient, for example. But with the physics-informed neural network, where the physics is acting as a regularizer, you are able to track this change in the neural network, in this gradient. So what I have shown here, these three curves are showing the comparison between the exact result and the prediction using neural network. And you see, neural network is giving you almost result with 0 error, and for all the time steps. Now, this problem is a one-dimensional problem, so it may seem that it is very easy to solve, but just try to solve this problem using finite element. You will realize that this is not a simple problem because there is at t equal to 0.5. So here, or around here, you see the gradient, there is a sharp change in the gradient here. And so, if you don't place many mesh points or many elements here, your neural network, your finite element will not be able to track this sharp change in the gradient. So you need a very fine mesh at x equal to 0. And only then will you be able to track this change. So this is not a trivial problem to solve. Now, this is a problem. So remember this slider I showed in the first slide. So like initial condition and boundary condition, that's all. But so data is high. We have large amount of data. And that is why this slider is towards the right. So it is more of a computational science and engineering problem rather than a machine learning problem. Let us go to another problem. And this is the Navier-Stokes equation. This is a canonical problem. A flow past a 2D cylinder. And then this is your vorticity field. What we have is measurement of u and v. So basically the two velocities we have measured. And these are showing you the velocity measurements. And then what is the objective? Well, we assume that the governing equation is partially unknown to us. So for example, this is my governing equation. This term 0.01 is unknown to us. So we want to estimate this parameter. First objective. Second objective, we have measurements for velocities. Can I estimate the pressure? Remember, we have no measurement for pressure. We only have measurements for velocity. And we want to estimate the pressure. So this is a very challenging problem. And if you use a data-driven framework, you will not be able to solve it, period. This cannot be solved using a purely data-driven framework. But with a physics informed, you can, because this U and V are actually linked to this P pressure through this neural physics, which is partially known to us. So here are the results actually. So this is the predicted pressure. This is the exact pressure. And then the pattern looks exact. However, you see the range is different. So it may seem that we have failed in predicting the exact pressure, and the answer is yes. But This is coming from the problem definition itself. The exact pressure can only be reconstructed up to a certain additive constant. So for example, if you compute the mean field and subtract the mean field, these two will match exactly. As for the PDs, we have identified the PDs in an almost exact manner. So instead of 0.01, it is like 0.01047. So we are able to estimate the governing differential equation. I heard some sound. So is there some message or something? No, I guess, right? Okay, anyways. So that was Navier-Stokes equation. Now let us come back to structural analysis or structural mechanics. So what happened was we were solving those problems and we were getting huge success. So we thought, why not solve a fracture mechanics problem? So we tried to solve a fracture mechanics problem using neural network, and we failed miserably. The method which was working just fine for Berger's equation, which was working fine for Navier-Stokes equation, did not give correct result when it comes to fracture mechanics. So we went back to the drawing board and started thinking that why is it failing? So anyways, so we will come to that in a while, that how we can solve that part or how we did solve the fracture mechanics problem. But before that, let me define the problem. So if you ignore this G phi term, this is your classical stress equilibrium equation. Minus grad dot sigma stress is equal to F. Now this G phi is there because as the fracture propagates, there is a degradation in the property, and this G phi is representing that degradation. Now what is this phi? Phi is known as phase field, and phi tracks how the fracture is propagating. Wherever there is fracture, this phi value will take a value 1, and away from the fracture it will take a value 0, and then it is a continuous variable between 0 and 1. The evolution of this variable phi is again tracked by this nonlinear differential equation, where G we call it as the degradation function, T I told you is the phase field, there is GC which is the critical energy release rate, material property, L naught is the characteristic length of your fracture, of your crack, which is here, H is there, which is the, and this is a coupled system we are looking into. You cannot solve this equation on its own. There is a coupled PDE and you need to solve them simultaneously. Now, what is this history function? Well, history function is basically defined in terms of the tensile strain energy functional, and initial history is defined in terms of the distance from the crack. So at the initial value t equal to 0, the history function is defined based on distance from this crack that you see on the figure on the right. And the objective is to use physics-informed neural network, physics-informed deep learning to solve this fracture mechanics problem. So what are the challenges? Why we failed? Because initially we failed. We could not solve this by minimizing the residual. Well, first challenge is there is a history function present. So whatever response you observe in the current displacement step is dependent on what was the displacement in the previous step. So you think about in time, you can think of the Rangakut fourth order RK method. So there, whatever response you obtain in the current step is dependent on the response at the previous step. So similarly like that. So presence of history function is a big challenge. Second, there is discontinuity. We are removing the discontinuity by bringing phase field, but still the displacement and stress field is extremely complex. And so what is happening is when you are trying to minimize the residual, neural network is not converging. So minimizing the residual R did not work for fracture mechanics problem, at least for us. So then what we do is we went back to the drawing board, we started reading literature on finite element method, and then we realized that modern finite element methods, or even finite element methods in general, do not directly minimize the residual of the problem. What it minimizes is the variational energy of the system. So in other words, instead of solving the problem in the strong form, we solve the differential equation in the weak form. So we brought this idea of variational energy into the neural network, and what we solved is variational energy based physics in form neural network. That is what we proposed. So here is the framework. So we represent u as a function of x. There is no time here, although there is a displacement step. And then what you can do is you can modify this neural network by multiplying it with certain factors so that the boundary conditions are automatically satisfied. For example, if your boundary is that at x equal to 0, your boundary should be 0, you multiply u with x, xu. Then if you substitute x to be equal to 0, u is always 0. Then what we do is we use automatic differentiation, that is what AD stands for, to compute ux, that is del u by del x, and also the higher order derivatives. And then we use these neural networks to formulate the physics informed neural network. The only change here is instead of residual on the right hand side, we have the variational energy of the system, or differential variational energy, which obviously you need to integrate over the whole domain. So this has to be integrated over the whole domain. And that is a challenging aspect. How to compute variational energy is challenging, or how to do the integration. Again, we went back to finite element. They use Gauss quadrature. So we use Gauss quadrature to integrate this variational energy over the problem domain. That is what we did. And here is the algorithm. It's same actually, that you start from some initial field, you assume u to be neural network, you compute ux, u double x, and then you do the same thing that was discussed earlier. The only problem is we are dealing with a fractured problem. So there is a for loop, and in each of this for loop, you see we minimize the loss to compute the neural network parameters. So the neural network parameters are to be computed at each displacement step, or at each loading step. That is expensive. If you are trying to solve neural network at each loading step, you are practically training hundreds of neural network, and not parallelly but serially. So that is very difficult. So training physics informed neural network for each load step is a challenge. And to address that challenge, what we proposed is known as transfer learning. So what is transfer learning? So think of it as neural network. And then after the first time step, so once you have trained the network, what we do is we fix these parameters. So these parameters will not be updated. Whatever we have obtained, that is fixed. And then for each displacement step, we only update parameters corresponding to the last layer. Now, whatever we have, so for these parameters that you see here, you can think of learning means these parameters are the ones that have the knowledge. When you minimize the residual or the variational energy, these parameters get tuned. So these parameters carry some knowledge. So we are transferring the knowledge of a current displacement step to the next displacement step by fixing this parameter. So this knowledge is conserved. We are not touching this knowledge. Whatever knowledge has been gained, we are reusing it. And this part is tuned to gain additional knowledge. So this is what we know, what we call as transfer learning. Transferring the learning from previous load step or displacement step to the next displacement step. And we used it for solving different types of problems, fracture mechanics problems. I'm going to show you two of them. So first one, this is again a canonical problem. So this is a beam with 3 holes that you see here. This portion is actually nonlinear. And then this is elastic and this is elastic. And then there is a crack here. You keep on increasing this load V, and then how this fracture path will propagate, how this fracture will propagate. And then this is the result that I'm showing you here. So you see the fracture is propagating through the second hole. And this is exactly matching with the experimental results. So physics informed neural network results are matching with the experimental results. So you can see that the results are quite accurate. If you want to know more about this example, you can refer to this article actually, where we have talked about how this is, or we have shown more results. There is one more example, and this is more challenging because in this case, there is no initial crack. So as you keep on increasing the load, what happens is that the crack first initiate and then it propagates. And even a crack initiation problem in 3D, we solved it using neural network and the results were matching with those in the literature. So you can actually solve fracture mechanics problem as well. Again, this is also given in the same literature, so you can have a look. Now, whatever we solved till now is kind of an improvement over finite element. So you can think that, okay, this will give you result more faster and maybe a little bit less accurate than finite element. But there is already something known as finite element. So there is a question that comes to your mind that why will someone want to use this framework? So now let us look into some problem where this is actually useful. And that is stochastic mechanics. That is mechanics where things are uncertain, things are not certain, where there is uncertainty. So you see, generally when you solve a problem, this is what you do. You provide some inputs like the loading, forces and all those things. You provide the parameters, elastic modulus, Poisson's ratio, and then you have a computational model like finite element method, and that will give you some predictions of displacement, responses like stresses, strains, and all those things. And that is what you and myself and everyone generally does. But the problem is these parameter values like elastic modulus, Poisson's ratio, these are actually not known to us. What we have to do is we have to go take a specimen of a material, perform laboratory experiments, and collect laboratory data. So this is your laboratory data, response data. And from those response data, we then have a measurement model. Basically, we solve an inverse problem to compute the parameters. Now, this measurement model is often not accurate. So the parameters are often not known at every location. And as a result, because of our lack of knowledge, because of heterogeneity in the material, because of unknown environment, because of changing scenarios, these parameters are uncertain in nature. So this X you see, both the input and the parameters are random variables. And if this X is a random variable, quite naturally, Y is going to be a random variable as well. And this is what a stochastic mechanics problem deals with. That how we can propagate from this X, the uncertainty in X can be propagated to the uncertainty in Y. That is what the stochastic mechanics subject deals with. So what are the research questions we look into in this domain? Well, uncertainty quantification, reliability analysis, risk analysis, reliability-based design optimization, robust design optimization, robust control. All of these are problems which deals with stochastic mechanics. So we will be looking into stochastic mechanics from one problem point of view, and that is basically reliability analysis point of view. Other things can automatically be done using this framework, but we will not go there. We will only talk about reliability. So before I go into reliability, there is little bit maths here. So let me first define the notations and all those things. So you see xi here. Wherever you see xi, that is my random variable or stochastic variable. And then if you draw a sample from this xi, that is this little xi, that is realization of stochastic variable. That is a sample drawn from this stochastic variable. Now there is a concept of limit state function, and that is represented by using J. So if you have taken a reliability analysis course, you will know what the limit state function is. So basically, this function represents when a system is going to fail. And then for all the xi's, all the samples of this xi, for which the limit state function is indicating failure, is known as failure domain. So the failure domain is is all those xi's for which the limit state function is less than 0. So that is how we are defining the failure domain. And then if you see something like this, a capital F, capital Xi, and then in bracket Xi, so that is basically your cumulative distribution function of the input variable, or known as the CDF. So you know about PDF, this is CDF. You must know about this as well. Now using this notation, if I have to define probability of failure, this is how we do it. So what is the probability that a sample from this stochastic variable Xi will be in the failure domain? That is what this is saying. So for example, what is the probability that, so suppose E is our random variable. So what is the probability that for a certain E, my system will fail? Or my stress will increase the threshold limit provided by the IS standard. So think of it like that. And this probability of failure can be solved by solving an integral problem, a high dimensional integral problem, which is rewritten here in this form, where this I here is known as the delta function, which is something similar to Kronecker delta, which you learn in your continuum mechanics course. So this I is your delta function, and F is your CDF, and you are integrating over the whole domain. In the previous expression, you were integrating only over the failure domain. So this I will now filter out whatever is not in the failure domain. Now, what are the challenges? I mean, we have a closed form integral. I mean, we have an integral solution. This would be easy. Unfortunately, it is not easy. And the reason is this is a high dimensional integration problem with no analytical solution. And if you try to do it using numerical integration, that is what people do, you have to run your complex computer code thousands of times, sometimes even millions of times. So the limit state function, this one, which defines this failure domain or this indicator function, is in form of complex computer code, a finite element code. A single run can take days for a realistic system. And in that case, you cannot really hope to run this code more than 100 times. But to evaluate this probability of failure, that code needs to be run for millions of times. So that is not really an option. So these are the challenges. So here is the framework. So I talked about finite element code, and previously I said that finite element is a method for solving PDEs. So let us say this is my PDE. And this PDE is directly representing my limit state function. Now, what I want to do is I want to solve this thing, or I want to represent this limit state function by using a neural network. But the problem is now, along with this x and t, I have these random variables to deal with. These are not constant now. The random variables are going to change because they're random. So we go back to the physics informed framework that we discussed earlier. The only thing we're doing is that along with x and t, now my random variable is also an input. So that is the only modification I'm doing. So previously x and t were the inputs. Now the random parameter is also an input to the neural network. And neural network will give me u. I will satisfy the boundary condition, do automatic differentiation to compute derivative with respect to t. So this is time derivative. Do automatic differentiation to compute derivative with respect to space. Combine all of those, and that will give me the residual of the system. And if you minimize this residual, you have a neural network which is directly giving you the limit state function. So you see, we have formulated a neural network framework which needs no run of the finite element solver. So from zero data. And that is why we call this framework as simulation-free reliability analysis framework. And simulation is a big deal in reliability. The overarching goal in reliability is to minimize the simulation, and we are proposing a framework where no simulation is needed. So let us see how this one works. The framework is more or less same as before. So this is a simple problem, only one random variable z, which is normally distributed with mu and sigma, which is given here. This is basically the diffusion equation. And then we solved it using different methods. Now, for this particular problem, exact solution is known, but generally MCS is our benchmark. So, if MCS is our benchmark, the probability of failure is what? 0.0035. This is your probability of failure. The number of samples or number of FE runs, this is the one. So, you should have a look at this column and at this column. This column is a function of this one, and then this is giving you the error. And so you should also have a look at the error column. And now you can see that physics informed deep learning is giving you the minimum error with no function evaluation. So you know you don't need to run the solver even once. So from zero function evaluation, it is giving you highly accurate result, as accurate as the MCS, which is the benchmark. Other methods, form, sum, importance sampling. So all these are benchmark methods in literature, which are well established, and all of these are giving good results, but not the best result. The best result is being by PIDNN, both in terms of efficiency, because no function evaluation, and accuracy, because the minimum error. Now, this paper is currently under review, but a version is already on archive, so you can have a look, where we show that how you can solve a reliability analysis problem with no data. Now we solve another problem. Now this is a problem from a biological point of view. So like how our cell will produce enzymes if I stimulate it, but you don't need to look at it from a biological point of view. You can think of it from a differential equation point of view. Like these kinds of equations are very common even in structural engineering. So like we have three equations, coupled equations, and we have what? In this case, we have 6 random variables. And this is my limit state function, which is a function of this thing, which is coming from the differential equation. And the objective is to compute the reliability index and the probability of failure. Again, taken from the same paper. So here are the results. So you see the MCS result is again matching exactly with the physics informed result, that is our method, while other methods are little bit off, not significantly, but little bit off. But more importantly, this kind of accuracy is obtained with no simulation. So you don't perform any simulation. You don't solve the differential equation even once using finite element or a time integration scheme in this case. And then in this case, we have varied the threshold value. So basically this value we are varying to see whether our method is robust or not. And we are comparing with MCS, which is our benchmark, and more or less the method is found to be robust. Now, coming to the last part. Now we talked about physics informed neural network. We talked about physics informed Gaussian process. But in both these cases, there was one assumption that we were making. And the assumption is that the governing physics of the problem is known to us. But what is the reality? The reality is that the governing physics is known to us, is true, but it is also true that the governing physics is only known in an approximate sense. So I talked about beam theory, but those beam theories are based on certain assumptions. You must have studied the course on solid mechanics or theory of elasticity. And the first assumption is the material is isotropic homogeneous. The second assumption is plane section before bending remains plane after bending. And then with this assumption, you are finding out the differential equations. So the differential equations are based on certain assumptions which are not true. So the differential equations are actually approximate. Yes, in lab, you can perform experiment and you can collect data. Those data are actually exact. The equations are approximate because those are based on certain assumptions. So in this framework, we talk about a realistic scenario actually, and that realistic scenario is exact. So there is a grammatical mistake. This should be exact. So exact physical laws are almost always approximate in nature. So in a real life scenario, you have an approximate governing equation, which is important, which give you useful information, but which is not exact. And then you can perform experiment to collect data, but the data is also limited. There are only a few experiments you can perform. And even if you want to perform simulations of real life things, those are time consuming. So we are in a situation where if you use this approximate governing equation, which we were doing until now, the results will not be that accurate because this equation itself is an approximate. And on the other hand, we have a scenario where we have very few data, and you cannot hope that only with this few data, which are accurate data nonetheless, you can have or you can build a neural network which is exact. So the question we are asking is it possible to exploit the best of the two? Can I exploit this highly accurate limited data and combine it with this approximate physics? And that is, the answer is yes, and that is what I will be talking about now. So here is the idea. So what do we do? The answer is yes. Now, there is no proof that this is going to work, no theoretical proof that this works, but for practical problems, we found out that this is working, and we are working on bringing out some proof that why this is working. But the proof part is still missing. But yeah, experimentally or numerically, we have shown that this works. So we talked about transfer learning, and that is the same thing we are going to do. So first you have the approximate physics, basically this one. First you have this one. You use this one, use the concept of physics informed neural network, which we used to train a neural network. So this is the exact same thing which we have been talking about for the last 45 minutes or so. And then you have this neural network. What you do is you have learned something from the physics. So you want to preserve those, so you fix these parameters. So transfer learning again. The parameters in the YOLO box are fixed. And then you take your data, this data, and then you are only going to train this network for this data, and your neural network parameters corresponding to the last layer, that is in the green box, is only going to get updated. So basically, learn from the low fidelity equation, then use transfer learning to preserve those knowledge while updating some portion of the knowledge by using the data that you have. And since we are using both low fidelity and high fidelity, this is known as multi-fidelity. Fidelity means accuracy. So this is low accurate physics. This is highly accurate data. Both to train our neural network. In case you have enough high fidelity data, the top portion will become useless. So if data is available in abundance, you don't need the first part, mostly. But in case your data is very limited, you need both of this part. And that is the idea. So coming to the last part of the talk, so basically we revisit the same example that was solved earlier, but in this case we make a certain modification. So now everything is random. So we have 13 random variables. Previously we had 6, so that is one change. The parameters that are shown in red have been changed. So K was previously deterministic, now it is random. G4 previously was 0, now it is 2. And IT, which is the signal that we are providing to the cell. So you can think of I as the forcing function. So this IT is going to vary. So what is going to happen is, for the low fidelity model, IT is equal to 0. And if you put IT to be equal to 0, you see this thing will vanish. And what you have is only this portion. So basically the equations are getting decoupled, and many of the random variables are also vanishing. And for the high fidelity case, I equal to 2. And then the question is, can we compute the reliability similarly as before? And it seems the answer is yes, we can do it. And here is your result. So what we have compared with, let us see. So this is the MCS result, the gold standard, the ground truth, the benchmark results, right? Now, what happens if you only train with the low fidelity physics? Because now the physics is different from this MCS. You will get erroneous results, and that is obvious. There is a 64% error. What happens if you use your limited data? Since data available is very less, neural network is unable to learn, and there is 100%, close to 100% error. And then when you use both the low fidelity physics and high fidelity data, you are getting almost exact result. There is a 1.52% error, but like 0.16 and 0.17. That is the range we are dealing with. And you can also change the threshold as before, and you can see that the method is still robust. And as I said, in this case, okay, these are the mean parameters, and there was 10% variation. And this paper is already published actually this year only, so you can have a look in this paper and at how this thing is working out. Now we did one more case study, and that was that this was a time-dependent problem, right? There is some dependence on time. So how the method is working across different time. So like 2.7 to 3.3, 4.7 to 5.3, 8.7 to 9.3, and 6.7 to 7.3. And we have plotted probability of failure, and you can see it is giving quite accurate results throughout different time. For each of this time, different thresholds were used, so that is given here. So lastly, let me conclude. So what we talked about today is essentially this diagram. This is the diagram that we talked about. So first we talked about Gaussian process latent force model. And there it was basically given this data, how can I estimate this input? So if we start from here and we go here. And that was the first part of the talk, that how we can use Gaussian process latent force model or physics informed GP to estimate the input function. Then in the second part, we talked about this part. Forget about this to PDF. So from input to output, how we can go from the input to the output by using physics informed neural network. That was the second part. One part in that physics informed neural network was also that how we can go from here to here and from here to here. Like this whole cycle was covered in the Navier-Stokes problem that we discussed. And then lastly, we talked about a scenario where this X is basically uncertain. So X is not perfectly known, and how we can propagate this uncertainty in X to Y and compute probability of failure. And then lastly, we talked about a multi-fidelity framework where this is not accurate. We have some data and how both of these can be used to go from the input to the output. So essentially every aspect of this diagram that you see in this talk actually. So I will stop here actually, and any questions you might have, any discussion you want to have, we can have a discussion now. So thank you, and any question is actually welcome.
Thank you, Dr. Souvik. Dear participants, if you want to interact with sir and have any queries, please ask. Okay, I think you want to please. Okay. So I think the participant needs some time to ask you questions. So I hope they will ask you later. So I'm having the contact detail of Dr. Souvik Chakravati, and as well as it is available on the website of IIT Delhi. So with the permission of Dr. Souvik Chakravati, I can share his contact detail with you if you have any doubt in the future, and you can ask and interact with sir. Uh, thank you very much, sir, for presenting this comprehensive lecture related to computational mechanics. I also want to congratulate you for the newly opened center at IIT Delhi, that is the Center for Scientific Computing and Computational Mechanics. So the students now having one more option to carry out research in this area because the center is available at IIT Delhi. Sir, you started the lecture with the very basic and stressing on the challenges associated with the uh, machine learning. Then expanded your ideas over some engineering problems that are related to fracture mechanics, dynamics, beam bending, and even biological problem. Thank you very much, sir, for giving us such a beautiful and informative lecture. And we hope that the participant will also carry out research in this particular area in the near future. At the end, I would like to request you to, sir, say a few lines about the newly opened center at IIT Delhi, so that the students come to know what is the objective and how it
Okay,
can.
so first of all, I think there is a miscommunication. So that center is actually not a center. That is my research group. Okay, that
Okay,
is basically I am the only one, and my students are the only one who are working there.
okay,
So what we are looking into is basically like whatever I talked about, like computational mechanics from a different angle. So how machine learning, deep learning can help us in solving computational mechanics problem. For example, there is a new concept of digital twin that I did not talk about that we are looking into. So what is a digital twin? Digital twin, you can think of it as a digital replication of an actual physical system. And with like modern sensors and all those things, data is continuously be collected from the smart city, smart infrastructure that can go into your computer and that can result in, and your computer model can be continuously updated. So basically, what you are seeing on your computer is a real-time thing of what is there in the field. So that is like a twin. So that is why the name digital twin. So that is also one area we are looking into. But we did open something here. We opened a new thing here at IIT Delhi, which is School of AI. That website is not up yet. So we are working here actually. So that is, we have opened a School of Artificial Intelligence. Around 22 faculties are involved there. And the idea is to work on XY, that X plus AI. And what is this X? This X can be computational mechanics, it can be structural engineering, it can be civil engineering, it can be geotech and all those parts of civil engineering. It can be healthcare, it can be robotics. So basically, every places where AI can be helpful, we are looking into that. So that is actually something we are really positive about. And also another thing, I don't know whether you guys know or not, but we also started our new BTech program at Department of Applied Mechanics. So that new BTech program is on uh, computational and engineering mechanics. So, or engineering and ECM, engineering and computational mechanics. So this year the first batch has joined actually, and the response is quite positive. But that is also something you can look into. And in this course, the ECM, we are actually teaching like machine learning in our to our BTech students, robotics to our BTech students, multi-scale modeling to our BTech students, parallel computing, high performance computing, and all those things, the modern things are being taught to the BTech students. So it's not like now this is no longer a research topic. BTech students are getting exposed to this thing. That is again something you will find on the Department of Applied Mechanics website, and that is, I think, will be of interest to at least some of you. So I will stop here. I think other information you will be able to find on the website actually.
okay. Thank you very much, sir, for giving us the idea about this department and the newly opened center. Thank you very much for accepting our invitation in the very short time and giving this very informative lecture in this 5 days ESTC. Thank you very much, sir.
Thank you for inviting me. Actually, this was a nice experience. Hopefully, this pandemic was not there. That way, we could have interacted more.
Yes, yes, definitely, sir.
And many of the students or attendees may not know that Dr. Bhimol is actually my batchmate from PhD. Like we are like batchmates in IIT. So
Yes.
yeah. So anyways, so it would have been nice to meet him as well. Anyways, okay. Thank you.
Okay, thank you, Dr. Souvik. Thank you. Okay, dear participants, the next lecture in this series of the 5 days ESTC will be delivered by Dr. Aditya Singh Rajput. He is the faculty in the Department of Civil Engineering, IIT Ropar, and I also believe that the next lecture will be a very good lecture of this series. Thank you. So we will again meet at 3:30 p.m. Thank you.